Hey, I hope you all are safe with your families. Now, first of all, congratulations for qualifying for the limit. Like a very large number of students gave the exam, and very few got selected. So, you're among those. So, keep it up. Now, we are going to talk about rationals and reals and sequences in them. Okay. Now, before starting with these, I must quickly brief you about what are we going to cover in this discussion. So first we'll talk about what a real number is. Number is, and then we'll briefly talk about the rational numbers. Then we will do some talk about. I'll just introduce to you to what symbols and some frequently used symbols and terms are, and after that we will give some examples of sequences in naturals and what a sequence mean in any given set. Then we'll talk about sequences in rationals, and then we'll talk about convergence or the limit of sequences. Then after that we will talk about Cauchy sequences. What they are and the Cauchy sequences in rationals. Then after doing Cauchy sequences in rationals, giving some examples of them in rationals and what they are in rationals, then we'll move on to we'll again come back to that irrationals and reals. Okay. Now after that we will talk about some important results. But before that we can still Cauchy sequences. Sequences in reals, and then we will discuss some important results and Bolzano Weierstrass theorem. After that, we'll talk about what limit superior and limit inferior are towards the end of the lecture. And in the end, I'm asked to introduce you infinite series. All right. So this is pretty much what we are going to discuss in this lecture. So now, suppose that you have a line and you also have a set S, some set S with some elements. Can you think of such a set S in which there are elements such that no matter what length I give you on this line, you can give me a corresponding unique element in this set S which can represent it. Okay? Do you get it? No matter what length I give you, you give me a element to represent it, an unique element to represent every length possible. Can you? Well, such a set is uh, we know such a set. It's called the set of real numbers. For those who are in class 8 might not know it, set of real number is the name given to that continuous quantity which can be used to express lengths or distances. So let's see how they look on a line. Okay. So first we have what is called a unit length. You take a length of a choice and you call it a unit length. Okay. Now you make folds of it, like two folds of it, three folds of it, and so on. And you have the counting numbers, which set this set is represented by capital N. Okay. You include 0, and in the opposite direction you take the same unit length and you call it -1, -1, and you take folds of it again to create the set of integers, right, denoted by capital Z. Now you also have lengths which are of the form like which are fractions. So it's half of the unit length, one fourth of the unit length, right? One fourth of the unit. How do you represent them? For example, you have 3/4. To represent it, you make 4 equal divisions of the unit length. Okay, and you count one from here, three from here, 1, 2, 3. What about similarly 7 with 15 can be done. You make 15 equal division over here, and you count 7 from there, and you have 7 or 15. For numbers greater than 1, say 7 by 3, either you divide the 7, the length corresponding to the 7, into 3 equal parts and count 1, or else you can see it as 2 plus 1 by 3. And you can count 1, 2, and make 3 equal parts, and 1 over 3 is this. Or one more way is it can be written as 7 times the length of 1/3. So you make 1/3, 3 equal segments on each unit length, 1, 2, 3, and you count 7 from here, 1, 2, 3, 4, 5, 6, 7, 7 by 3, right? So in this way you can represent all such numbers. These numbers are called um, rational numbers. Okay, these are denoted by capital Q. These are set of all numbers which are the form P by Q, where P and Q are integers and Q not equal to 0. Now, if we have the set of all such numbers called rational numbers, let's see how they look like, how they're distributed over the number line. Okay. So, one thing to observe from the integers is the fact that given two any integers you take, 7 and -1 you say, there are always a finite number of integers between them. Also, the minimum distance between two given integers can be just a unit length, right? No matter what integers you take, you cannot have a distance between them less than unit, right? But is that true for rationals? No, right? So let's see how they are actually distributed over the number line and how many rationals can you have in two given rationals. So suppose you have two rationals positioned on the number line, say A and B. let's do an activity over here. Okay, you divide it in n equal parts. Okay, now you can name the first one. You know these all these are these pointed elements or the or numbers are real, and all these are rationals as well as right. How? Well, you can each length can be written as b minus a over n. And before doing this, one thing to note is the fact that given in two rationals, say x and y, there no matter what you no matter you multiply them, you add them, or you subtract them, they'll always still be a rational, right? You can prove it, right? Take x and y with p by p1 and q1, p2 by q2, and show that they still are integers, integers over integers, and the denominator is not zero. Okay. Now all these are rationals, right? So how? This length is b minus a over n. So to produce what to know this what this rational number is, you can just add b minus a over n to a. Similarly for this, you can say that it is a plus 2 times b minus over n, and similarly. So you are adding basically two rationals. So these all are rational numbers. But hey, this n was arbitrary, right? You can take arbitrarily large n. So you can create more and more divisions, as many as divisions you want. So for n, there are n numbers between them. So as you make n minus 1 rational numbers between them. So you can make n a larger and larger and create more and more rational over here. It represent more and more rationals over here. And this doesn't depend on how the gap between the a and b, right? So no matter how fine you have a gap, how fine a segment you have in the number line, there are always an infinite number of rationals between them. And so for example, in that gap you make infinitely many such segments, a lot of segments, and even on those segments there are infinitely many rational numbers. So that is true for any segment on the number line. So suppose you are taking you making such fine segments all over the number line. So you know that in each segment there are infinitely many rational numbers. So it seems that all the rational numbers, like this number line, is fully covered with rational numbers. But is it continuously covered with rational numbers, or are there gaps, or are there numbers which are not rationals, reals but not rationals? Well, there are. Not only there are much more bigger set. Okay, we'll talk about them. What's left on the number line is much more of a bigger set. Okay. So hey there. So now we'll be discussing some terms and symbols. But before doing that, do you remember a few minutes ago I told you that whatever left on the number line is much more of a bigger set than what set of rational number is? You would say that, but set of rational number is infinitely big. It contains infinite number of elements. And then you would say, then what's left on the number line, set of all that, must be infinitely big. It must contain an infinite number of elements. You're right. Then you would say, but wait a second. Are some infinities greater than others? Doesn't that mean that? Maybe. I mean, in some sense, yes. What I actually meant was the set of rational numbers is at least listable. What does that mean? It means that you can make such a list of rational numbers such that this list contains all the rational numbers. right? For example, you say 35 to the 17, it is going to be somewhere on the list, no matter which rational number you want to choose, right? But for set of what's left on the number line, if you go on making such a list, you you'll find some elements missing, no matter how you make it. There are going to be elements such that they are not in the list. Not only some, but infinitely many. Okay, so in a sense, at least the rational numbers are listable, and those are unlistable. Therefore, in a sense, they are bigger set. Now, the symbols, right? First, we have belongs to. So, for example, 2 belongs to set of natural numbers, right? Then we have for all. For example, consider a set S of elements greater than 1, and 1 is less than or equal to less than x for all x in belongs to S, right? Right. Now you have there exist. And the last symbol such that. So let's make use of these. Consider the set as this again. Now there exists n belong to set S such that 2 to the n plus 1 is a prime number, right? There exists such n, right? For example, n is 2, 3, 5. So these are the symbols. Now we will be discussing about some important terms that we'll be using frequently in the later part of the discussion. What are those? First, consider set S of real number, non-empty real number, non-empty set of real numbers. Now this set will be called as bounded set, bounded above if there exist, let's say, small s such that for all x belonging to S, small s is greater than or equal to x, right? If there is exist an element, a real number, which is greater than or equal to all elements in this S, then it is called bounded above. And this S will be called an upper bound of S. Now, similarly, we have lower bounded below. What is that? There is S dash if when a set S will be called as a bound below if there is exist similarly I have also if there exists S such that for all x in capital S there exists small s such as greater than or equal to x, then this set is called bounded above. Now we have set when will a S set of real numbers will be called bounded below, it will be called so if there is a s dash such that for all x belonging to capital S dash is smaller than or equal to x. So if there is a real number which is smaller than every element of the capital S, then it will call bounded below. And such a number S dash will be called a lower bound of capital S. It is right now. Also, it will be called a bounded set if there exists small s such that small s is greater than or equal to modulus of x for all x belonging to capital S. So if there exists a number which is both greater than, like, if you can find s and minus s such that s is greater than every element from the set capital S and minus s is smaller than every element in the capital S, then we say that the set is bounded set. Now we also have a supremum or the least upper bound, right? So this should make it very much clear what supremum is. So as the name suggests, a small v will be said to be a supremum of set S if first v is an upper bound of S capital S. Also, if u is any upper bound of set S, then u must be greater than or equal to v. So it is the least of all upper bounds for set S. Then this v is called the supremum of the set S. Now, similarly, we have infimum or the greatest lower bound. What is that? If that v dash will be called an infimum, will be called the infimum of the set S if v dash is a lower bound also if u dash is any lower bound of capital S, then u dash must be smaller than v dash, right? So it is greatest among all the lower bounds. So these are the pretty much all the terms. Like how many there are? 7, right? that we're going to be frequently using. So you must not be entirely unfamiliar with the word sequence. You have seen sequences in prime. You have seen, suppose I give a boxes, give boxes, and I ask you to count the number of squares, 5 and 14, right? This is also example of sequence. You also have heard about the Fibonacci sequence, apparently the most celebrated sequence in mathematics, uh, in which the initial two terms are given to you, and the next term you generate by adding the previous two terms. So 1 plus 1 is 2, 2 plus 1 is 3, 5, 5 plus 3 is 8, 8 plus 5 is 13, and so on. So these were some examples of sequences in naturals. Now a sequence can be in any set, right? This need not to be only in naturals. So for defining a sequence, what a sequence is over any set, as it is defined as a function whose domain is a set of natural numbers and whose range is contained in set S. Okay. So for example, if you have say set S as @gmail stickman alpha and so on. An example of sequence would be like f1 equals 0, f2 equals f3 equals stickman, f4 equals alpha, and so on. And also you can represent it in the horizontal fashion like these, as first term is gmail, second term is alpha, and stickman and so on, right? So this was sequence in any set, any given set. And when the set S, if you replace the set S by a set of rational numbers, you have sequences in rationals. Okay. Can come with some examples of sequences in rationals. Say 1 over n. The terms will be 1, 1 half, 1 third, and so on, right? Say 10 to the n minus 1 over 10 to the n. The terms would be 9 over 10, 99 over 100, 999 over 1, 3 zeros, and so on. Okay. Now, what else? You can have n square over n square minus 1. You can have 3 over 2 to the n, or 2 over 3 to the n, or even 1 minus 1 to the n over 2, or anything. These are some examples of sequences and rationals. So let's talk about what is meant by the convergent sequence. Now let's see. Now you see that as a sequence progresses, for example this sequence, you see this term is getting more and more closer to 1. How? If you write that, if it is quite more apparent if you write in terms of decimal form, is 0.9, 0.99, 0.999. And it seems that if the sequence goes on forever, this term would never contain a 1. Like this sequence will never contain a term called 1, but eventually it is getting closer and closer, more closer to the number 1. So we say that this sequence is converging to 1, right? Or else we can say also the limit. The limit of the sequence is 1. Okay. That is limit or the convergence of the sequence. So can you give me where this sequence is converging? Similarly, this sequence can also be seen as converging to 1. How? You can write it as 1 minus, it is greater than 1, so 1 plus 1 over n square minus 1, right? And we can see that it is 1 over 1 square minus 1, that is. The first term is undefined over here, so we start with the second term, the 2 square minus 1. And then we have 1 plus 1 over 3 square minus 1 and so on. You see, as the n is growing larger and larger, this term is getting bigger and bigger, right? N square is getting bigger and bigger. So this whole term is getting more closer to 0. We'll talk about how this is happening. First, let's talk about other examples. We'll talk in more detail when this is getting to 0. And okay, so let's talk about this for now. So here, you see, all the terms of the sequence, no matter what n is, this number is always greater than n. Can you show it? You can show it using the mathematical induction, right? Okay. You can show that it is true for all n belonging to a set of naturals, right? 3 by 2 is greater than 1, 9 by 4, which is 2 plus 2.25, is greater than 2, and so on. What about this sequence? Well, since this is true, we can write it as equivalent. This inequation can be written as 1 over n is greater than 1 over 2 by 3 to the n, or 2 by 3 to the n, right? These terms, and you already know that this term is getting closer and closer to 0 as the sequence progresses. We will see how it is true, but for now, just assume that it is in fact going or converging to 0. In a minute, we'll show that how it is actually going to 0. We'll prove it that no matter what epsilon you take in a set of rationals, for now, you can always find n such that 1 over n is less than epsilon and positive. Okay. And hence we'll be able to show that in fact this is convergent. This is the, I'll come back to it in a few minutes. For now, let's see this. So this in fact is getting, this also seems to be going to 0. It will prove how it is going. And if you talk about this, if you go on writing the terms of this sequence, it will be something like for n equals 1 it is 1, for n equals 2 is 0, again for n equals 3 it is 1, again 0, 1, 0, and so on. So if you say that it is converging to someone, that is not going to happen, because either is never getting closer to n as a number, right? Neither it will ever be 1, it will ever get closer to 1 or to 0, so it is not converging. So those sequences which are not convergent, we call them a divergent sequence. So this is also an example of divergent, because this is not converging to any number on the number line, any real number. Even this is not converging to any real number, so it is also a divergent. All other on this list are convergent, right? I'll show it how. So let's now talk about the 1 over n. Right? And what limit and what convergence of a sequence means. Let me define it properly for you. So for that, let me first define to you what tail of a sequence is. Okay? So suppose I have a sequence. A sequence can be, in a standard way, it is represented as x equals xn. Okay, where n belongs to next number. Or it is also represented as an ordered tuple x1, x2, and so on. Now, in this, what a tail of a sequence is, if you remove a finite number of elements from the head of the sequence, say you remove 3 elements from here, then what you are left with, the sequence, is called the tail of the sequence. Okay? So in this example, it is called a 3-tailed. Okay? In general, if you have a sequence of reals as this, and you are removing an n number of n terms of the sequence from the head, removing all the n first n terms, then you are left with this sequence. The left sequence is known as the n tail. Okay? So this is what a tail of a sequence is, and what is n tail, right? Okay. Now, so before defining what a limit is, let's do an activity. Let's play a game. In this game, I'll give you a number called epsilon. Actually, a real number, epsilon, which is positive. And for all that epsilon, you will be giving me a natural number. We will call it h of epsilon. Okay? Belong to a set of natural numbers. Such that in this sequence, the h epsilon tail, all the terms of the h epsilon tail will be at a distance less than epsilon from 0. Okay? Such that all the terms of the h epsilon tail will be at a distance less than epsilon and 0. Okay. So if you are able to give me an h epsilon which is naturally, so that h epsilon tail, all the terms of the h epsilon tail will be at a distance less than epsilon from 0, then you will say the sequence is convergent to 0. Okay. For example, if I give you epsilon to be 0.01, can you think of an h epsilon such that h epsilon tail of the sequence all the terms over here would be at a distance less than epsilon from 0. So what it means that h epsilon plus k minus 0, what is this? Is less than epsilon for all k. Right. Doesn't that mean? Okay. So if you are able to give me such an epsilon, h epsilon, for every epsilon I give you, then it is called converging to 0, or the limit of the sequence will be called as 0. Fine. So can you give me an h epsilon for every epsilon? Suppose that epsilon is 0.01. What epsilon should take such that every term of the h epsilon tail would be less than 0, less than epsilon distance from 0. So take h epsilon to be 100. And you'll be done with it, right? How? If you take h epsilon to 100, the h tail, the h epsilon tail, or the 100 tail would look like 102, and so on, right? Let's see if every term of the sequence is a distance less than epsilon from 0. So let's suppose 101. Distance from 0, is it less than epsilon? Yes, it is, right? 1 over 100 is greater than 1 over 101. Similarly, every number sequence is less than 0.01, right? So for 0.01, you are able to provide me with such an h epsilon. But can you give me h epsilon for every epsilon given? When? Okay, that is the question. Even if you take it to be 0.000, say 5 times or say 700 times. 0, then 1. So what should be a choice of h epsilon? Well, you can take h epsilon as number of zeros plus 1. So 701. Right? Right? You guys can check how that is true. Now, let me prove that for all epsilon there exists an entity at least. Actually, we have talked about 0.01 and 0.701. Let's talk about all epsilons in general. Okay, so for now, let's talk about epsilon. Those epsilon which are rationals. Later on, we will, after talking about the rationals and irrationals and reals, we will show how that is true for all real epsilons. For all epsilon belonging to rational numbers, epsilon greater than 0, we have to prove that this sequence and rational number is convergent. So the distance from the end tail. If we show this, then we'll be able to resolve since 1 over n is greater than 1 over n is greater than 1 over n plus 2. This will be true for all n plus 1 plus 2. Every term of the sequence will be less than epsilon distance only 0. Right? So we prove for 1 over n. So the question is, can you find an n for every epsilon? We have to prove this, right? So for that, let's see a proof, like see a thing. You know that for all x in rational numbers, you can always give me natural number, small below natural number, such that x is less than that natural number, right? You can always give me natural number which is greater than given rational number. Okay? So if that is true, if x was of your choice, you can take x to be 1 over epsilon. Okay? And here also epsilon is of your choice, right? So here, consider it is less than 1 over n. Rearrangement will be like other equivalent form since epsilon is greater than 0. And take x to be 0 for now at least. If epsilon is greater than 0, here epsilon is greater than 0 and is also greater than 0. So the equivalent form of this equation would be 1 over epsilon. And we'll have it there. Right, the proof of this. Right. And first of all, how is every rational number less than a given? How is a given rational number is less than every natural number, isn't it? How can you really find a natural number greater than every rational number given? Yes, because certain natural numbers are unbounded. Let's see the proof for rationals. See, x is lower, right? If you take the n equals 1, then you see that n is always than here. Therefore, you can always find an n for every x you have. Now we can say that 1 over n, the sequence 1 over n, converges to 0. Okay. What about other examples? What does a convergence mean? This was a convergence for 0. In general, what a convergence means is a sequence xn is said to have a limit say small x if every if for all epsilon greater than 0 there exists a natural number such that for all a numbers x n plus a minus small x plus epsilon. Right? If the distance of every term of the n tail, you see this is an n tail. If the distance from every term of the n tail of small x is less than epsilon, then we'll say that sequence has a limit x, or the sequence is said to converge. Right? There is a general definition of what a convergence of the sequence is. Let's talk about whether these sequences are converging or not. Just proof of them. Here is the definition. So here, if we talk about an n tail would look like this can be written as 1 minus 1 over 2. So we will show that this is converging to 1. Okay. To show that, you will need to show that x of n plus a minus 1 minus this sign for within 0. And so now we have done for n. Okay. This, if we are able to say this, then we are done, right? This term is 1 minus 1 times 3 and plus 8. Right? Okay. Now, one thing we know that 10 to the n is always limited. How? We can use induction to show that. In fact, for any number greater than 1, you can show that x to the n is greater than 1. Can you show that by induction? Right? So for 10 to the n greater than n, we know that from this. So okay, but we also learn for every epsilon greater than 0, there exists n belong to the set of natural numbers such that number is less than epsilon. Okay. So if this is true, this has to be true, right? From here, if this is true, then we can also have the convergent to the n plus 3, which must also be true. write it as. We can add, we can do this, right? No problem with this. Here there is no problem. We can add 1 and subtract 1. And we have the required equation. Right. And hence we will say that this sequence is converging to 1 because its distance, every term of the sequence is less than epsilon distance from 1. Okay? Now let's talk about other examples. You can do the same thing for n square over n square minus 1. How? You can make sure that we write the same as 1 plus 1 over n square minus 1. And show that n square minus 1 is greater than for all n greater than 2 and equal to 12. So if this is true, then you can say that 1 over n is greater than 1 over n. And you are dealing with 1 over n is less than epsilon for all epsilon equal to 0. So it's this and 1 over n square minus 1. And again adding another subtracting one. This, which is the required equation, right? Same thing to the over here. Now, if we talk about this, this does not converge to any because for all n greater than 0, 3 over n, so then is greater than n. So it is not converge into any relation number, any number actually. So any real number. So what we see here is the fact that no matter what, suppose it is converging to n x, but you can always give an example of an n which is greater than x. Greater than x, right? And it is greater than 0. So it contradicts the fact that 3 by 2, 3 over 2 to n is greater than or that converges to x. So it's a divergent sequence which does not converge to any real number. It's called divergent sequence. So is this, because it is again not converging to any real number. Hence it is again a divergent. Okay. Now what about this? You already know that 3 over 2 to be is greater than n. Implies that 1 over n is greater than 2 over 3. And this is greater than, oh, you also want 4 over n natural. And for all epsilon greater than 0, you can find natural number such that 1 over n is less than epsilon positive. Therefore, this equation, from this equation here, which would mean that for all epsilon 0, there is this. That is true. Okay. So it will mean that. So we have shown that the sequence converges to 0. So we see that these sequence converges and rest which are these two do not. Okay, so these two are the example of convergent sequence and these two of diverging. Let's once more visit the previous sequence, uh, which we used as an example to show convergent sequences. So 1 over n terms which are 1, 1 half, 1 third, 1 fourth, 1 fifth, 1 sixth, and so on. Now let us plot these numbers on the number line to see how they look like. Suppose we have 1 here, we'll have somewhere over here 1 third, 1 fourth, 1 fifth, 1 sixth, 1 seventh, 1 eighth, 1 ninth, 1 tenth, 1 11th, 1 12th, 1 13th, 1 14th, 1 15th, and all the next numbers are between 0 and 115th, right? So we said that 1 over n is a convergent sequence, and it meant that no matter how small you take your epsilon, you can always find an n such that such that the whole entail will be all elements of entail, all elements of entail will be less than epsilon distance apart from 0, right? Or from the limit for 0. For in this case, it is 0, right? So we apparently can see here, right? It is quite visible here that you can always, if no matter how small you take an epsilon, I can find an entail. This is the entail, right? In this case, it is 11 or 10 actually. For this epsilon, it is 10 NSN. So 10 tail for this epsilon. So no matter how small epsilon you take, you can always find an entail such that all the elements of it are less than epsilon distance apart from 0, right? So one more important thing to note over here is the fact that as the sequence progresses, for all epsilon greater than 0, as the sequence progresses, all the terms of the sequence gets closer and closer, and until it vanishes almost. They get arbitrarily close, no matter for all epsilon, right? They, for example, what I actually meant by saying is that for all epsilon greater than 0, there exists n in natural numbers such that such that any two pair of entail will be at most epsilon distance apart. If I can write in terms of expression, it would be something like k1 minus x of n plus k2. These two are the terms of k1 and k2 are arbitrarily chosen. Like you can take any k1 and k2 such that they belong in natural number. So these two are the elements of the entail. Now the difference, the distance, would be less than epsilon for all epsilon greater than 0. Okay, and for, for all k1, k2 belong to natural numbers. Is what I meant. So in this case, even can we show that 1 over n is such a sequence? Let's see that if it is true or not. So in 1 over n, we can say that we have to show that this is true, right? So for xn for 1 by n is just 1 over n, right? So We know that 1 over n is between 0 and epsilon. For a given any epsilon, I can find always n, at least one n, such that this holds, right? For every epsilon you give me, I can always find over n such that 1 over n is less than epsilon and positive, right? And we also know that 1 over n plus k1 is greater than 1 over n plus k2 if k1 is greater than k1 is less than k2. And one more inequality we can form over here is the less than 1 over n, right? Yes. And from here we have epsilon. Since it is true for any epsilon, given it should be true for epsilon by 2 as well, right? So we can form over here, right? Now we can say from here, from these inequalities is the fact that k2 is less than epsilon, right? But we also know that there's something much more smaller than this, which is 1 over n1 plus k1 minus 1 over n k2, right? This thing is smaller than 1 over n plus k1 plus 1 over n plus k2, right? These are two positive numbers added. This is the difference between two positive numbers and taken modulus, right? We know that this is true. So, so this must be true. From these two inequalities, we can conclude that is an epsilon. Hence, 1 over n is such a sequence in which terms get arbitrarily close as the sequence progresses, right? So, yes. So such a sequence is called such a sequence in which the terms get arbitrary closed not just like any two pair of the entail gets arbitrarily closed, then we call such a sequence as a Cauchy sequence, right? I'll just write what a Cauchy sequence is. A Cauchy sequence, right? It's a very important sequence in analysis and topology. It's a very important sequence. So, Cauchy sequence, what it is? Um, Suppose x equals xn is a sequence, right? So, if for all epsilon greater than 0, there exist n belonging to natural numbers such that xn plus k1 minus xn plus k2 or less than epsilon for all k1 and k2 belonging to a natural number, we we say the sequence as a Cauchy sequence, right? So if as the sequence progresses, any two terms of the sequence get arbitrarily close, we call that sequence a Cauchy sequence. Now let's talk about few rational numbers. So let's take 3 rational numbers, 22 over 7, 4 over 3, and 4 over 5. Let's see the decimal expansion. So it is, what it is, 3.142857 4428 and 7. This repeats. For this, it is 1.33. This repeats, and for this, it is 0.8 terminated. Do you know that all rational numbers are either of these two forms? Either some band of digits will repeat or it will just terminate. Can you prove that? Can you prove that all rational numbers are only of these two kinds? And now consider a circular disc. I painted it with ink exactly half of it, right? Now I rolled it without sliding on a line, right? I rolled it, and this ink got printed over here. Okay, I took a scale and measured it. So the following sequence were given by that scale, depending on the precision: 3, 3.1, 3.14, 3.141, 3.1415. Similarly, one more construction, let's do it. Take a line at an angle of 45 degrees from the horizontal axis. You make an ray. Now on this ray, from this point, you take a unit distance, create a perpendicular to it, and mark the point on the horizontal line. Now we'll be measuring this length. So you measured it again using a length. So depending upon its precision, you again wrote it in terms of sequence. Like this. Do you know what if I tell you that this sequence of rational numbers will go on forever, and this will not even terminate or repeat any of its band? Weird, right? What's weird is this number, when the sequence has a sufficiently large number of elements, the digit might contain a phone number. Actually, if it is sufficiently large number of sequences are produced, it will contain your phone number, right? Now, can you also show that these two sequences are Cauchy sequences? I can give you a hint. See, every time you are adding a new term without disturbing the previous term. So you are adding, for example, for here, the difference between these two is 4 10 to the power minus 2, right? Here 1 times 10 to the minus 3, and the power of 10 is decreasing every time you add, and so on. Difference between these two is this, difference between these two is this. Similarly for this case. So can you see the difference is decreasing? But we also can see that this is a Cauchy sequence. Can you prove it? Well, prove this, try this and try that. It's not tough to prove that it's a Cauchy sequence. In fact, a Cauchy sequence. Now let's talk about this length. So since this is in unit length, this 45, this is 90, but by triangle sum property, we have 45 degrees again. Some of the interior angles are equal, some sides are also equal. These both are 1 units. Now we have this a right angle triangle. So we know by Pythagoras theorem, let's call this x. So square of hypotenuse is equal to sum of the square of the sides. Therefore we have x square equals to. Now the first question which comes to mind, since this is not terminating anywhere, is it possible to write in terms of some rational number? So let's assume that this is actually a rational number. So let x equals p by q. What do we have here? P over q square equals 2. P square equals to q square. Now consider this equation. Since the right hand side of the equation is even, it must be even. A square of odd cannot be even. Now, first of all, I must say that we have taken P and Q to be co-prime. Now here, both sides are even. So P must be even. P cannot, if P was odd square cannot be an even number. Therefore, P must be an even number. So we have P is even. Now here, since a perfect square, if you square an even number, it will always be a multiple of 4, right? So this must be a multiple of 4. Since already 2 is a factor, here q square must be a multiple of 2. So a perfect odd square cannot be multiple of 2, therefore q must also be even. But hey, we took p and q to be co-prime. So there must be something wrong. So our only supposition is wrong here, which is we took p over q to be x to be p over q for some integers p and q, right? Yes. So there are no rational number when squared equals to 2. Right? So there are some length which can be constructed on the number line, which cannot be expressed in terms of rational numbers. Now we have seen here that on a real number line, there are not only length, which can only be represented in terms of rational numbers, but also lengths which cannot be represented in terms of rational numbers. So we call them irrational for the fact that they cannot be presented in terms of ratio of two integers. So what we have in the number line, including the rational and irrational, is now a quantity that is continuously covering the number line, and we call this now a real number line. And all the set of all these numbers is called real numbers, right? So it is a quantity, it is a continuous quantity that can be used to express length or possible length in a number line, right? All possible distances. So that is a real number, and this line is called the real number line. So we talked about convergent sequences, we talked about Cauchy sequences, and we took example of 1 over n, and we said that it is a convergent sequence because it has a limit and it converges to 0. Similarly, we talked about some examples like this, and also and then we talked about this, right? Now we see that we also saw that 1 over n is not just convergent, but it also is a Cauchy sequence. That is, if you take an n-tail, that is, for all epsilon, you can take an n-tail such that any two terms of that n-tail would be at a distance less than epsilon. Okay? But we proved this for 1 over n. Can we prove this for any convergent sequence? Is this true for all convergent sequences which are convergent? It turns out yes. All convergent sequences are Cauchy. And also, all Cauchy sequences are also convergent. I'll prove the first part and I'll leave the later part for you. Okay? So let's prove that all convergent sequences are Cauchy. So if we have a convergent sequence, it would be like for all epsilon greater than 0, you can find n equals h of epsilon by 2 such that xn, any term of the tail would be at a distance less than epsilon by 2 from x, from the limit point, from the limit, right? Now let's take for all cable. Right? Now let's take two such keys. So from the two such elements on the entail K1, it will be true for all the elements, and it must be true for this, and it must be true for the other K as well. Right? Now we know for all real numbers, for all A and B belong to set of real numbers, we can show that modulus of A plus modulus of B is greater than or equal to mod of A. Right? Okay. Using this theorem, we are going to prove it. Now we'll add these two. We'll have this inequality, and we know this thing is greater than the difference of these, right? Or perhaps it must be visible for you, right? Which can be alternatively written as just the difference of these two, right? Epsilon, less than epsilon, right? This is the required thing, right? So this is a Cauchy. So these are, as K1 and K2 are arbitrary, the difference between two is less than epsilon. So it means any two element you take from the entail, it will always be at a distance less than epsilon. They will always be at a distance less than epsilon. So all convergent sequences are Cauchy. Now I leave you the proof of the converse to you. Okay, I leave the proof of the converse for you. Proof of the converse. And hence all Cauchy will be convergent and all convergent will be Cauchy. Now we also have a term called the subsequences. Now the some term suggests it feels like it is a subset of the sequence. So it is, suppose there was sequence xn, which elements are x1, x2, x3, x4, x5, and so on. Suppose I have some natural numbers n1, n2, n3, n4. The sequence defined by as xn1, xn2, xn3, xn4, and so on is called a subsequence of the sequence x derived from these. Okay, so what can you give? I'll just give an example of such a sequence. For example, you have a set of sequences of prime. I'll just select the numbers at the event position. So 3, 7, 13, and so on. This is a subsequence. Other example, suppose you have the this convergent sequence 1 by n, So its terms are 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so on. I'll take one from the odd and one from the even, next even, right? 1 over 4, then 1 over 5, then 1 over 6, 1 over 8, then 1 over 9, like this. So this is also a subsequence of the given sequence. Okay, no matter what number element I'm selecting. So we talked about Cauchy sequences and how they are. Same method, convergent sequences, right? And we also talked about subsequences, what they are. Now let's try to understand what are the different types of divergent sequences. Now these are mainly of two types. First type is that in which every subsequence of the sequence grows larger and larger unboundedly, then we call it as properly divergent. So not only just larger and larger, if it is unbounded, or the subsequence is unbounded, then we call it as properly divergent. So it can grow larger on the right hand side, or it can go larger in amplitude from the left side. In the left side, it could go to minus infinity. Right? Here the properly divergent sequence says, right? N minus n example. Now we also have those sequences in which the subsequence might converge. For example, minus into the n. You see? Right? So, if you take this subsequence at the odd position, it is convergent to minus 1. And if you take at the even position, these are convergent to 1. So both the subsequences are convergent. So let's take another example of such case. For example, we have 3, 1, 1, 1.4, 3.1, 1 over 2, and 3.14, 1.41, and 1 over 2, 1.414, 3.141, 1 3.1415, 1.4142, 1 over 5, 1 over 6, 3.1459, and 1.4141. So this you have this sequence. Now you see that this is a bounded sequence. Why? Because all the subsequents are convergent somewhere. Which subsequence? For example, this 3, 3.1, 3.14, 3.141, 3.1415, 3.141. This subsequence is converging to pi. Right? First subsequence is 3, 3.1, 3.14, 3.141, 3.1415, 3.1415, convergent to pi. Other sequence note 1, 1.1, 1.4, 1.41, 1.414, 1.4142. Second subsequence. Square root of 2. And the left one is, you can say, 1, 1/2, 1/3, 1/4, to 0. So you see that all the subsequents of it are converging to 0, right? So if we have a sequence, so first of all these are convergent. So these can be termed as pi, root 2 and 0. All these are not limit but subsequential limits of the sequence. Or, or in other words, you can say limit points. Let's see how they look on the number line. Okay. So, that's number 1. You have 0, 1, 2, 1, 12, and we have 1.4. Root 2, square root of 2, 1, you have 5, right? You have 0. Now, first term 3. Then you have second term is 1, third term is 1, then 1.4. Right. Then you have half. 3.14, then you have 1.41, then 1 over 3, then 1.414, then 3.414, 3.141, then 1/4, then you have 3.1415, and again this. So as the sequence is progressing, these terms are getting denser and denser here, here, and here, right? At pi. So these can be termed as points which have subsequential limits. So these are called as limit points. Okay. Fine. Now we'll be studying about more. We have a name for greatest of all these limit points. We'll talk about that while talking about limit superior, and the least one also we have term for it. It's called limit superior, but we'll not be using this definition. We'll be using in the beginning we'll be using a different definition, and we'll see how it is equivalent to this. So let us now quickly look at an example. If you now tell me whether it is a Gaussian sequence or not. Fine. So a sequence defined by a function as nth term as root square root of n. Now, if you talk about consecutive terms of it, the difference between consecutive terms would be, which can be written after rationalizing as, fine, as n grows larger and larger, both these quantities grows unboundedly, and therefore this must tend to 0 as n grows. So as n grows, 1 over root n plus square root of n plus 1 must tend to 0. This is true, but this wasn't the definition of the Cauchy sequence. That is not how we claim a sequence to be a Cauchy sequence. Rather, we see that any two pair of the entail, the difference between them decreases. The difference between them is less than epsilon if we take sufficiently large n, right? For a given epsilon, we can take an entail such that any pair of such entail term, any two term we take from the entail, the difference is at most epsilon, right? So what it was, epsilon greater than 0, there is n belonging to set of natural numbers such that x of n plus k1 minus x n plus k2 is less than epsilon for all k1, unique to belongs to natural numbers. If this happens, then it is true, right? So just try it if it is a Cauchy sequence or not. Now we'll get back to the previous example. We talked about irrational numbers, which were mm, described in terms of a Cauchy sequence and rational numbers. Otherwise, one. Great. Now see, one thing to notice over here, these two sets, these two function sequences are bounded sequences. Why? Because all the terms are less than 2, less than 4 over here in this sequence, and in this sequence all the terms are less than 2. Okay. Also, these are increasing functions, increasing sequences. So they are monotonically increasing. Okay. What third thing we know? Both are both are first bounded, second monotonically increasing, or say just they are monotonic. They are monotonics. They are monotone sequence, right? In this case, they are monotonically increasing. They are monotone sequences, right? So, can we say that all sequences which have these two properties must converge, as these two are converging to some irrational numbers, right? So can we say this is true for all sequences? If these two are the, the observation, if we get then that sequence, we can say that they must converge. Well, yes. This is called the monotonous or monotonic convergence theorem, right? It's called as monotone convergence theorem. What this tells us is the fact that if you have a sequence xn and this is monotonically increasing or decreasing, this is monotone, and also if it is bounded, then then it must converge. Also, it tells us that if a sequence is monotone, and convergent, then it must be bounded. So I'll leave it to you. I will leave it, the proof I will leave it for you. And we'll now move on to two important theorems. First one is monotone subsequence theorem. And the second, Bolzano-Weierstrass theorem. So the first two very important theorem. We are now progressing towards the end of the lecture. So the first one is monotone subsequence theorem. What does this theorem tell us is that given any sequence you have, no matter if it is monotonous or what, just a sequence, it will every time always have a subsequence which is monotonous, which is monotonically increasing or decreasing. So any subsequence, every subsequence must have a every sequence must have a subsequence which is monotonically, which is monotonous. What is monotone? It is monotone. This is what it tells us. So I'll just prove it for you. So let's see. Now for now, if I'll just define a term. If uh, xn is greater than xk for all n greater than equal to k in the sequence, if given sequence is this, right? If in the sequence, if the nth term is greater than all the kth term which are greater than nth, which means that if xn is here, xn plus 1 is the next term, xn plus 2 is the next term, and this xn is greater than all these terms, then this number, this xn is called peak. Just a name I'm giving it, right? So, given any sequence, it might have a finite number of peak, or finite, which includes zero, or it can contain an infinite number of peaks. Right. So I'll prove that in both cases there are subsequences which converge. Okay. So if first I'll prove for the infinite number of peaks. So if there are infinite number of peaks, for example, if say xn is one of the peak, and it means that for it is the greatest of all the other coming uh, terms of the sequence. So it must be lesser than the next. So let's suppose that m1, the peaks occur at m1, m2, m3, and so on. This also is an infinite sequence of natural numbers, right? Because peaks occur infinite number of times. So you can easily say that xm1 must be greater than xm2. Why? Because xm1 is a peak, right? So it must be greater than all the terms following it. Similarly, xm2 is a peak, it must be greater than all the terms following it. Similarly, this. So you see that there is a subsequence which has been created over here, which is monotonous. In fact, monotonically decreasing. Okay. Now we'll prove for the other case for the finite number of peaks if you have. So I'll just rub this part. So suppose that it has finite number of peaks. So say so let's if it has finite number of peaks, then there must be some peak. We'll just take the last peak. Say xm is the last peak. It must have a last peak, right? Because it has finite number of peaks, it must have some last peak. So let's say for m, xm is a last peak. So now we'll look at the m tail. Right. This part has no peak. Okay. Now, since it has no peak, first term will take at x plus 1. Since it is not the peak, it means there must be some number greater than it, right? Because if there were no numbers greater than it, it would mean that it is the peak. So there must be some number greater than it. So say xm plus k1. Okay. So again, this is not a peak. because there are no peaks in this, right? So again, we can say that xm, there must be some m plus k2 which will be greater than this. Similarly, we can find infinitely many such terms, and hence we have a subsequence over here, which is in fact monotonous and monotonically increasing. So hence we prove that every sequence must have a subsequence which is monotone, or the monotone subsequence theorem. So just now we talked about two important theorems. The first one was the monotone convergence theorem. Okay? Okay. So what it says was, if you have a convergent, a monotone, and it is convergent, then it means it must be bounded. And also, if you have a monotone and it is bounded, then it must be convergent. Right? So it says that monotone sequence is convergent if and only if it is bounded, right? So if I have a monotone and if it is, let's say, bounded, if it is bounded, then it must be convergent. That's what this theorem says. Now we talked about another important theorem, which was the monotone subsequence theorem. What does this say? It says that given a sequence, it must have a subsequence which is monotone. It must have sequence it always has a monotone subsequence. And we proved it. Proof of this was given for you, and this was proved for you, right? Now we have another important result, which is the Bolzano-Weierstrass theorem. Okay? We'll talk about this now, and how we, using these two theorems, we can prove it. Okay? So let me just write what a Bolzano-Weierstrass theorem is. Spelling might be wrong. Bolzano-Weierstrass theorem. What it says is, given a bounded sequence, you always have a convergent subsequence. Okay? Given a bounded sequence, you can always find a convergent subsequence. Okay, how? Uh, it is not very difficult to prove. If you know these two theorems, this follows from it. Like, so suppose I have a bounded sequence. Since all sequences have a monotone subsequence, this bounded sequence must also have a monotone subsequence. And if you talk about that bounded monotone subsequence, you know that a bounded monotone sequence is convergent, right? So that subsequence will be convergent, right? Okay. So this was the proof of Bolzano-Weierstrass theorem. Now we'll talk about uh, the last part, which was the limit superior and limit inferior. So here, suppose that you have a bounded sequence X. Okay. Now, suppose that you also have a set V such that, consider a set V such that this V is a set of all small v belong to the set of real numbers such that V is less than Xn or at most finitely many n belong to set of natural numbers. Okay, so V is less than finitely many terms of the sequence X, right? Okay, so if we have such a set V, then we say that, then we define a term called limit superior or the lim sup of the sequence X as the infimum of the set V. Okay, so let's see how this look like on the example we took while defining the subsequential limits. In that example, the subsequential limits were 0, square root of 2 was one of the subsequential limit. Then we had pi as one of the subsequential limit, right? So, so we had three subsequential limits there. One was pi, converging to pi. Another subsequence was uh, square root of 2, converging to square root of 2, and the third sequence was 1 over n, converging to 0. Now let's suppose there are two more subsequents to it and two more subsequential limit to this, so that we could clearly understand what limit superior actually mean. So let's have the subsequence x4 as say 4 plus 1 over n, right? So first term is 5, then we have 4 plus half, 9 over 2, then 4 plus 1 over 3, then 4 plus 1 over 4, and so on. This will converge to 4, right? 1 over n will convert to 0, so 4 plus 0 is 4. So let's take one more example, one more subsequence to the sequence. the bounded sequence. So let it be -1 over n. Okay. So the first term of it would be -2 -3 by 2 -1 by 3 -1 by 4 and so on. So it converts to 4. Sorry, -1. Okay, because 1 over n would tend to 0 and it will be left with -1. So how would these subsequential limit? So suppose there are subsequential limit for the sequence x over xn. Okay. Now also, how would these look like on the normal line? So for x1, the first term of the subsequence would be starting from 3. In 3.14 somewhere over here, 3.1 and 3.14, getting closer and closer to it. The terms also, the distance between respective terms will also decrease, and they'll finally get closer and closer to pi. For the subsequence number 2, we have square root of 2. So first term would be 1, then 1.1, 1.14, then 1.1414. Similarly, if we again go slowly towards root 2. Third sequence, similarly, we have 1, then we have half, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, 1/9. This also will converge to 0. The fourth subsequence, 4 here and 5 here. First term will be 5, then we'll have 4.5, then again 4 plus 1/3, 4 plus 1/4, 1/5, 1/6, 7th, so on. It will also converge to 4, or you have to converge, and it will converge to 4. Now let's talk about -1, -2. So the fifth subsequence is converging to -1, right? So first term is -2, then we have -3 over 2, and again this subsequence 2 has a limit of converges and has a limit -1. Now let's talk about what limit superior is in this case. So let's talk about what the set V is in this case. So V is less than a finitely many number of terms, right? So if you take any real number, small v, if you, let's check any number between 3 and 4 is included in V or not, right? Let's see the selected number is in V or not, capital V or not, right? So for that, is it less than finitely many terms of the sequence? No. There are infinitely many terms here, right? Therefore, this would not be contained inside V. What about something greater than 4? No matter where you take, what number you take, greater than 4, it will always be less than finitely many terms of the sequence, right? See, no matter where we cut, there will always be finitely many terms in the right? So, even if you take 5 as a small v, it will contain 0 elements. There will be 0. So, 0 is also a finite number, right? Therefore, v equals 5 will also work. What about any number greater than 5? It will also work because there are 0 elements after that. So what we conclude that except for whatever number we take greater than 4, it will be contained in a set V. And whatever, and only these only this set will be set V. None of the elements will be in set V. Because if we take any element from here, then that element will be greater than infinitely many terms of the sequence. Right? So we conclude that this is our capital V, the set. All this collection of these continuous numbers is our capital V. And what is the infimum of V? The least upper bound, right? Least or the greatest. We have to talk about infimum, right? So infimum was the greatest lower bound. So all these are lower bound of this set, and greatest lower bound is 4. So we have infimum of this case of x plus 4. Okay, and hence the limit superior will be, sorry, infimum of set v is 4, and limit superior of the set xn is also 4 by this, right? Now let's talk what's one more term. Let's see one more term. Yeah. Similarly, we have a bounded sequence xn, and we have a set v of all those small v belonging to real numbers such that v is greater than xn for finitely many terms of the sequence. Then, then we define a term called limit inferior, or simply limit lim inf. Okay, what is lim inf? We define it as equal to the supremum of the set capital V. Okay, so let's talk about what this small number small v can be. So if it is greater than minus 1 anywhere here, suppose here, then it will be greater than infinitely many terms of the sequence, right? Because there are infinitely many terms over here converging to minus 1, right? So it must be smaller than minus 1. And you see that no matter what number you take less than minus 1, you'll always have finitely many terms over here. So again, like in that case, capital V will be the set of all elements from minus infinity to minus 1, not including 1, minus 1, right? So it will be this continuous set except minus 1. Because if we take minus 1, there are only many numbers less than minus 1, which are in this sequence. Okay, so the supremum, that is the least upper bound. All these are upper bound of the set, but the least upper bound is minus 1, right? So the supremum of capital V over here would be minus 1, and hence the limit inferior would be minus 1, right? Now, one important thing to note over here is the fact that in this case, uh, limit superior is in fact the supremum of the set of all subsequential limit. Okay, can you show that this is in fact true for all sequence we take? Any bounded sequence we take, if they have subsequential limits, then the supremum of those set of subsequential limits would in fact be the limit superior. So can you show that this is in fact the case, that limit superior is in fact the supremum of set of all subsequential limits, and similarly limit inferior is in fact the infimum to the set of all subsequential limits. It is easy to observe now. We can easily observe this fact of it, right? So now this will be a simple introduction of what infinite series are. So suppose you have a series given with x plus xn. Now an infinite series or just series is a sequence generated by this sequence in the following manner. See, so for S1 it is just x1, S2 is sum of x equals x2, S3 is sum of 3 terms. S3 would be and so on, right? So that's pretty much what infinite series are. Now let's talk some terms related to it. So these x1, x2, x3 are called the terms of the series. These are called the partial sums of the series. Okay. And we also have, if the limit of this set S, limit of the sequence S defined as this exists, then we say the series is convergent. It is a convergent series. Otherwise it is called as divergent series. So what are the examples? Some examples of series. So one example is the geometric series generated by the sequence defined as okay. So how will this SKS 1 to look like? R1 minus R minus R plus R square Q minus 1, right? So this is pretty much what a geometric series is. And then we have, let's talk about what are the notations used for a series. So use sigma, just we can write it down of this generating sequence simply as x1 or also sometimes as okay. So this is infinite series and some terms are limited.